All right, welcome back to another editions on practicing International Math Olympiads. So today I have a pre-selected certain questions um, that that may give us a good revisions practice, not only for Olympiad math but for your examinations also. All right, let's take a look at the first question. So this question is from the Korean Mathematics Competitions 2000 here. All right. So now let 3/4 less than a, where a is less than 1. So we need to prove that the equations given as such has four distinct real solutions and find these solutions in its explicit form. All right. So let's see how to do this. Right, let's try to explore the detail on how to work with this. All right, so this is a given conditions for A. It must satisfy this restriction for these equations to have four distinct real solutions there. All right. Now there are many ways to work with this. Now if you try to expand this, you will end up with quadratic equations, which is pretty tough to actually go around, right? So one way to do it is by uh, my way, that I call it relaxing and then moving forward. Right, so let's look at how to relax this equation. So first of all, we can actually expand both sides, so you get x4. Okay, that's what we have here. And then the other side here, you would tend to get a square, and I think that would be a 3ax, and then finally you have the 2x squared there. Right. Now, other than representing this as a polynomial equations in terms of x, we can also represent this sort of restructure this so that these equations can be written as a polynomial equations in terms of a. All right, so that's exactly what we are going to do here. So that will be 2x minus x3 minus x4 equals 0, right? So it can be restructured in such a way. And then from here, we can work out the discriminant. So the discriminant is b squared minus 4ac here. So our b will be 3a squared minus 4a, and then the c will be here. All right, so let's take a look at what we have here. Um, Oops, I think I did it wrongly. Hold on. All right, let's take a look at how to work with this. Right, now we have been given a restriction here. So this is one of the restriction related to A. So now we just need to prove that the equation here has four distinct real solutions. Right, now this is the way we go about proving that. First of all, we're going to expand both sides. So we have we'll get this one here. So if you all right. And then by rearranging that in this way, it could be a functions, a polynomial functions in terms of x. We can also arrange it in such a way that it could be a polynomial in terms of a instead. So I'm going to arrange it in this way then. So arrange it as a polynomial. In this case, it's just a quadratic. Okay, and then thereafter we can work out its discriminant, b squared minus 4ac here, which is 3x. All right, so from here you have 9x squared x okay, and then from here we can sort of simplify to 4x cubed plus 4x3 plus x squared here. And then of course the usual way is you can factorize it first, for instance. Okay, this way. And then thereafter, we can factorize it again if we can. So from here is quite obvious, is this. And then thereafter, we can simplify it as this. And then finally, we can write as 2x squared plus x squared. Alright, so I hope the first part is okay. Then using this result here, we can indirectly deduce that the A would have this solution here. Alright, so that would be the square root of the discriminant, which would actually be 2x squared plus x here divided by 2. Right? So therefore, we have two solutions for A. Case 1 here. So case 1, we will let A equal to 3x, 2x squared plus x divided by 2. So from here, we will be able to get like, this is negative 4, so negative 2x, negative x squared. So that's our first solutions there. All right, and then from here, we can rearrange that again in quadratic form. So there's 2x plus a equal to 0. And then solving this quadratic equation in terms of x, we will be able to obtain the solution for x as negative 2. That will be a 2, 1 minus a, then square root divided by a 2. So therefore, the x is 1 minus a. Alright, now this is the explicit, the first explicit solutions to this equation here. Now, I'm not sure whether this equation is correct yet, but later on we're going to identify all the 4 distinct real solutions, and then we're going to check that it does satisfy that restriction. Alright, now I'm going to show you the next case shortly. Alright, so here I have written down our first solutions here, and then this is our previous equations, A, the solution for A in this case. So we're going to consider the second case. So case number 2. So for case number 2, A would be equal to negative 3 plus 2x squared, 3x, right? Plus x divided by 2. Right. Now that would actually give us x squared minus x. Right. So let me check whether that is correct. So that's an x squared minus 2 minus x, yes, correct. Right. So from here we can rearrange that neatly. So from here we can get the other two solutions for x, which is 1 here, and then 1 minus, so 1 minus 4a here divided by 2. Alright, so these are all our solutions. So I'm going to write down all our solutions side by side so you can see here. I'm going to write it down this way, it'll be easier. Done. I'm going to write it down separately, 4 solutions here. Hold on, b squared minus, did I do it correctly? Oh, reset. This is a negative. I just noticed that. Let me change that. There's a negative, so therefore this is positive here. Yeah, so there will be a positive. Okay. Well, luckily I recognized the error there. Finally, we have this one here. All right. Now those are the 4. Those are the 4 solutions. Now we know that this must be less than this one here, and then this must be less than this, and then finally this one must be less than this one here. Right, due to the restriction that has been set here. Okay, Now, therefore, we can say that there are four distinct real roots or solutions here, right? Because these are all real, right? In this case, and then we also notice that there's a last part that we want to check also. So we also notice that um, 1 minus 1 plus 4a, yep, divided by 2 is greater than negative 1 plus 1 minus a here. Okay, so that's what happened. Now we can try to simplify this. Let me give you a try, see whether it works or not. If it's not, we're going to choose a second option here. So, all right, and then finally I will have there's a 3 more than a 2, 1 minus here. All right, so from here I'm going to square both sides. So I'm going to square both sides. Therefore, I will have here, I'm going to change the color here. So that will be a 6. Oops, I missed out one sections there, which is 1 plus 4a. Yeah, I should have been more careful with this. Just let me change that. So there will be another 1 plus 4a here. Okay, and then that should be greater than a 4 1 minus a here. Right. So there you have it. And then I'll try to simplify this. So you can see that. Let me see here. So I have 6 plus 4a. Right. So I'm going to bring this over the other side. Now that will be a less than. So I will have a 5, a 6. Okay, a 6 there. And then what do I have here? I have 8. So 8a. Okay. And then from here, I can try to further simplify that. That is basically this. All right. And then we can try to expand this one more time. Okay. So we can expand this one more time. All right. Now I'm going to write down at the at this side here so that you can see what is going on here. So I'm going to erase off all this. I'm going to write it down at this side so that it's easier for us to see. So from here, we have this less than 3 plus 4a here. Right, we're going to square it one more time. So there'll be a 9, there'll be a 24a plus a 16a squared here. Right, so therefore, I'm going to simplify that properly. So this is 36 here. So that will be 12a here. And then a 9 would basically cancel off. So greater than 0. And then you can further simplify this. Greater than 0, or we can actually write it down as this. Therefore, the solutions to this would be a must be greater than 3 over 4 there. And then knowing that a is less than 1, therefore that actually help us to verify the restriction there. Right, so I hope that you are clear with the first question. Now it is a utilizations of the knowledge of quadratic formula to solve this quartic equation. All right, so I'm going to move on to the next problem shortly. All right, second example. Here we are given a sequence for n greater than 1 such that the first sequence is 2, and then it satisfies this iterative formula for all n which are natural number. Right, now we need to find an explicit formula for an here. Right. Okay, so let me scroll it up a bit. Okay, let's try this out. Now the usual way to work with this is we try to figure out the solutions to this equation first before we continue on. Take for instance, Now there's a lot of trial errors going on. What I'm trying to present here is sort of the neat version of the result, right? So we can consider this. Okay. So we're going to consider, all right, so maybe I'll write down consider x equal to x over 2 plus 1 over x then. So where here I'm just letting my x equal to my an, right? So from here you will notice that there is actually half of x, 1 over x here. Therefore, indirectly we can find the solutions to x in this case. Shouldn't be that tough. You get a root 2 here. Okay, it's not 2 root to get the root 2. Plus or minus, don't forget the plus or minus. All right, now once we have obtained this, we can consider another fractions. All right, so as I said, this is the result of trial and error. So based on the result there, we can actually try out using this number here. So since there's a plus and minus, so we can try to work with this magical number here. So we're going to consider this particular ratio. Okay, so this one here is basically given by, if you look at this, an plus 1 is actually given by this. All right, now we can actually rearrange this properly. So that is basically an square plus a 2 divided by 2an. All right, now if you join the partial fractions together, so from here, we will be able to get a to the power of 2 plus a 2an plus a sub 2 divided by the same result here. Okay, divided by 2a, this is 2 here, sorry. Okay, and then minus sub 2 here. And then of course, doing a bit of algebra manipulation, we will be able to obtain an square plus 2 sub 2 an an plus 2 here divided by the same goal for the denominator, just that we have 2 sub 2 an plus a 2 here. All right, so that's how it looked like. And then okay, and then from here is pretty stunning, I would say. Now because there's a sub 2 here, because there's a sub 2 here, so therefore we can actually factorize this. That may not be your usual factorization procedure. If you notice this, you will say that, all right, it's very hard to actually factorize this manually, but actually you can factorize this, right? So the factor, if you factorize it properly, you should be able to get something like this. So if you square this, you are actually getting this one here, which is quite obvious. Right? So the same thing go for this, because there's a negative there, so therefore it's a square. And then by joining these two together, I can actually write down that as to the power of 2. All right. So therefore, I'm going to simplify all this, and then we can, I'm going to write that down again. This result is very beautiful, and then it's called iterative for a reason also. Later on you will see that. Okay, so I find this problem very interesting. All right, so this is the result that we get. We are going to make use of this result to find out the explicit formula for an. All right, stay tuned. All right, this is the result that we have obtained. Super important result. I'm going to show you why is it so, right? So I'm going to use a different color just to show you the result, or the result that we can obtain from here. So based on this, we can say that a2 when n is equal to 1, for instance. So let's start from here. So A2 will be this. That will be A1 plus this. Okay, you can see. All right. Now from here, when you try n equal to 2, of course, like I have too much time to spare here. Okay, so therefore, okay, so I can try with A3 now. So A3 simply is A2. Is this based on this result that we have obtained. But then again, we found that A2 plus square root of 2 divided by this is actually given by this. So therefore, we can further restructure this. So the internal expression is actually this, but the whole expression is raised to about 2. Then of course you can give it a try for 3 then. So I'm very curious with 4 now, because when your n is 3, so that is what we have. In this case, it will be A3 sub 2, A3 sub 2 also, a square. And A3 square is basically here. You can actually write this one down as, so if I were to simplify this, that is typically a 4. This is a 2. And then this one here, I'm going to substitute this one inside here. That will be A3, oops, it's not A3. It'll be A1 then. So A1 plus square root of 2 over A1. Now that will be 8, which is exactly the same as this one also. So I can see a pattern now at this point. So the pattern will be 2 raised to the power of 3 here, since n is equal to 3. This one I can also write down based on the pattern that I can, or the pattern that I can recognize here. So that is like 2 to the power of 2 now, since the n is equal to 2, right? And then this one here, I can actually write down as, if I want to sort of conjecture this at this point of time. Right, so there's 2 to the power of 1 there, 2 there, 3 there, and so on and so forth, of course. Right, so I'm going to show you the so on and so forth shortly. Right, so I've rearranged the result that we have obtained previously. This is the first result that we have obtained, and then um, by using the induction method that we have done. So this is the sort of the result that we have obtained, and then of course we can further continue on with this exploration. Take for instance, if your we will have like assuming that the term just before the n term, for instance. All right, so if I try this one n term here, oh sorry, I should be trying an. Okay, so if we try an, right, that must be the same as an minus 1. Yeah, an, this one must be an minus 1. An minus 1 minus this. Okay, this is when the n is actually equal to n minus 1. So this is I just write it down here. So it is n minus 1 here. All right, and then this for sure, this one will be to the power of 2, of course, based on this result here. But then again, we can further elaborate that. It will be the same as this, because you can see that A4 is raised to the power of 3 here when n is equal to 3. So this one here will be 2 raised to the power of n minus 1. And then there you have it. This is an plus square root of 2. Now, why is this important? Right, now you will see that here before we do anything, because our intention is still trying to get the explicit formula for an here. All right, so let's look at how to do that. Now this can be written as a1 plus square root of 2, a1 minus square root of 2. Now that is the same as 2 to the power of n by 2 to the power negative 1 here. Yeah, I hope that you are clear with this. And then we are given a1 here, which is a 2. So therefore, I can actually write that as 2 plus 2, 2 minus 2 here. And then this one can be written as a half by 2 to the power n. Right. And then from here, we can simplify this. Okay, we can simplify this. Right, now I'm going to simplify this here. So I'm going to put a star here to simplifying this. So consider this. So we're going to rationalize this. To rationalize this, we will get, in this case, you will get a 6, okay, plus a 4, cert 2, 2, 4, 6, yes, correct. And then here you get a 2. This is the one that we have here, right? Now, how about the square root of this result? How about the square root of this result? So the square root of this result, which is basically the root of this result. All right, here we can say that this root of this result can be written as a plus some form of cert, because no matter how you work with this, eventually there will be a cert here. Yeah, there will be cert. So we're going to let this equal to this in here. So from here, I'm going to solve for a. Now I'm going to do it here. Right, now you can see that that will be a squared plus 2a root 2 plus a 2. So I'm going to put my 2 over here. That will be the same as 3 plus 2 cert 2. Right. So by comparison, the coefficient for the cert and the constant itself, the one without the cert, we found that a is actually equal to a 1 there. All right. So therefore, this whole section here can be simplified into, so here I'm going to write it down here, can be simplified into something like this here. Now that will be 1 plus cert 2. So the whole thing inside here can be simplified into 1 plus cert 2, because this whole square root is 1 plus cert 2, and then raised to the power of n here. All right, I hope that is clear at this point. All right, now later on I'm going to conclude the explicit formula shortly. All right, this is the current result that we have obtained from here. So we found that this whole thing can be written in this form. Eventually, this lead us to this section here can be simplified into 1 plus 2. And then finally, we are going to raise this to the power of 2n here, right? So I hope that is clear at this point. Now from here, I'm going to focus on the more important sections without the intermediate section here. So therefore, I can concentrate on my analysis here. This is equal to this one here. Now 1 plus 2 raised to the power of 2n here. And then we can manipulate this algebraically. For instance, we can do it this way. Okay, it's rather confusing to write at this point of time. So basically, it looks something like this. Okay, and then that should be equal to an plus cert 2 here. All right, and then finally, of course, we try to combine the like term. So therefore, an is 1 plus 2 to the power n here minus 1. Okay, and then the other term I will bring it over the other side, so I can write down, I know that I can factorize this quite easily. N plus a 1 here. Alright, you can see that. So therefore, the explicit formula for an can be written as divide by minus 1. And then there you go. That will be the explicit formula here, right? I hope you will be able to understand the working behind this. Uses iterative formula and at the same time a bit of deductions involved, right? Now I'm going to move on to the next problem shortly. Right, let's take a look at our third problem, our last problem for today. Right, now these two exercises is on the products of sine trigonometry that involve a degree measure. Now the first one, find the smallest possible integer n such that it satisfies this equation here. It's actually a summation or series again. All right, let's take a look at the first question A here. All right. So this is a summation of a trigonometry series, and then we're going to prove that it's 1 over sine n, where the n is measured in degree. And then now hence we're going to make use of this result to prove B here. All right, let's get started with this. Now the first, firstly, let me scroll up so that I have more space to write here. Okay, for A, right. So we're going to start off with a very peculiar methods here. Personally, I find it very peculiar also. So we're going to start off by concentrating on sine 1 here. Okay, now that can be written as this. If you want to introduce the k inside, so that will be k plus 1 minus a k. Right. So from here we can apply the compound angle identity. So therefore we have cos k here minus of sine k cos k plus 1. Alright, and then by dividing both sides by sine k and sine k plus 1, so we have this. Right, so dividing both sides. Okay, so the same thing here, we're going to divide this by sine k plus 1 sine k Alright, so therefore we can simplify this as now that will be a cotangent, and then this one here you can see that there is also another cotangent. Alright, so that's one of our result that we can make use of because due to the subtraction ability here. Now to work with these summations, we're going to multiply both sides by sine 1 also. So you're going to multiply both sides by sine 1 degree. So the same thing here. Right, by sine 1 degree. So therefore, all this term here will be the same as this. So we can convert all this term into cotangent in this case. So therefore from here, I'm going to put a star here. So from this one, we can actually write as sine 1 degree over sine n degree, which is this one here, would be the same as the cotangent 45 degree minus of cotangent 46 degree. Okay. And then plus with cotangent, so that will be our first set, cotangent 47 minus with cotangent 48. Alright, and so on and so forth until we get a cotangent 133, subtract off with cotangent 134 here. Okay, alright. So I'm going to rewrite this one more time on top. So I hope that you can remember this result here. I'm going to move this onward so that I have more space to write here. Alright, so from here onward we can do some arrangement with the trigonometry ratio here. So take for instance, we're going to make use of the complementary rules, whereby the cotangent theta here is the same as negative cotan. Let me change that. So we're going to make use of the complementary rules. So that is actually negative cotan 180 minus of theta here. All right. So from here we can see that we can combine 46 degree with cotangent 134. So the sum of this angle must be 180 degree. And then after that we can combine cotangent 47 with cotangent 133 degree, and so on and so forth in this case. And then until we have until we reach 89 plus cotangent 91 here. And then finally we still have one more, which is cotangent 90 degree. So 89, so here 89, 91, and then finally there's the only one left here. Right? So cotangent 45 is actually a 1 here, and then you can see that this is actually cotangent 46 degree minus of cotangent 46. Alright, now the same goal for this 47 okay, and then finally we have the same thing here, cotangent 89 and cotangent 89 also. And then by the way, this cotangent 90 is actually equal to 0. So therefore the whole result will only end up with a 1 here. Therefore we can conclude that sine n is actually equal to sine 1 degree. Therefore the smallest n is equal to a 1 here. Alright, so I hope that is clear for the first question. Alright, our last sections for today. Alright, we're going to make use of our previous result there. Okay, so from here we have this is the sum of, okay, so here I'm going to write that down in general form. So that is the same as k plus 1 degree. So we are looking at the sum from k equal to 1 until 89 here. Okay, now this one can be written as sine 1 degree. So we can write it down as sine 1 degree here over sine k sine k plus 1. So that is the sum, 89 here. And then that would be the same as sine 1 degree cotangk k minus cotangk k plus 1 until 89. Alright. Okay, so that is basically the same as you'll notice that is actually cotangk 1 degree, and then subtract with cotangk 2 degree, and then after that plus cotangk 3 degree or 1 degree, and then whereas 2 is 2 degree, so that'll be 3 degree, and so on and so forth until we have cotangk 89 minus of cotangk 90 degree. Alright, so that is how it would actually look like. Okay, so from here we're going to rearrange again. You will notice that in this case we will only be able to get cotangk 1 degree here. Right, so cotangk 1 degree is basically this 1 degree sine 1 degree here. So therefore you have degree over sine square 1 degree. Therefore that complete the proof here. Right, so I hope that's clear.